Well, first of all, I want to talk about the DART mission. The DART mission was an interesting one. We launched a spacecraft, and the plan was to run into some stuff in space. It's not very often that we send a spacecraft out there, and the plan is, let's crash into a rock. Well, why would you want to do this? Why would you want to go crash into a rock? And there it is. Didymos is the bigger one, and there's actually a small moon orbiting Didymos called Dimorphos. And the plan was to hit the smaller one. So we were going for the bullseye, the tiny one. But why would we want to do and launch such a mission? Well, it turns out that a lot of asteroids cross Earth's orbit and could run into us and crash into us. Now, this one is not scheduled to run into Earth. There's no danger from it at all. But it does represent a class of asteroids that comes pretty close to Earth. And we want to find out, what if one did actually have our number, had our name on it, and was headed for us? What would we do? A lot of people say, well, just nuke it. Well, we don't know what a nuke would do. We don't even know what just running a spacecraft into it would do. That little moon has the mass of about 5 million kilograms, and the spacecraft is about 570, I think, if I remember right, kilograms. So the number difference is hugely different. It's a little tiny spacecraft and still a pretty big chunk or ball of rock. So what can we expect it to do? Well, from the moon's perspective, it might be thinking, oh, look, one of those cute little rovers is going to come take pictures of me. And the answer is no, that wasn't the plan, little asteroid. The plan is to run into you and try and change your orbit to see if we could nudge an asteroid aside. If one was coming at us, can we run into it with a spacecraft and just push it out of the way so it would miss us? It'd be a little bit like driving down the highway and having, you see you're headed towards a moth that's out there flying around in your headlights. Well, if you can get the moth just to fly a little bit higher, it's not going to hit your windscreen. It's going to go right over you. You just have to make a very small change. And we wanted to see, could we make that change? Now, how would we tell? Well, we picked an asteroid pair. Remember, I said it was a pair, two that are orbiting each other, because we can see one pass in front of the other one, and we can time that. So it gives us a very accurate amount of time of how long it takes for this one asteroid to orbit the other one. And if we change the velocity or the speed of the smaller one, well, then its orbit around the bigger asteroid will change, and we'll be able to measure it because they eclipse one another. So you can see some of these eclipses here. So let's take a look. They actually had cameras on board, and they captured this. So there's the pair of asteroids. We're headed at it. Now, it's a little bit jerky. These are independent photographs. They've stitched together to make a movie out of these. And we're getting closer, we're getting closer. So you can see it's very dramatic as we head towards it from this long distance. But this is pretty darn good targeting. These are small asteroids, and this was launched from Earth, of course. So as we approach, we can see the bigger one, the smaller one is there. Looks like we're on our way, and it's flat. Okay, so that let's Google and see if there's something out there that can show that a little more slowly. So, oh, Google. Yeah, so anyway, that was what Google had done about the DART mission. I quite liked it. We don't really need to Google this. Of course, we've prepared it. So let's run in fact, it is running. It's already running. Good. So run the slowed down one. And you can see we're heading towards that little moon. The larger moon off on the left-hand side, you start to see details in it. It indeed also looks kind of like a rubble pile, which is interesting, a big pile of rocks and dirt and dust. And as we get closer and closer to the small one, you'll even see on the end that's close to the big one, there's a rock sticking off the end there, glowing off the edge. So there must be a giant boulder there. And then we'll slow down the individual frames. Last frame there, and bam. The red is indicating there was no more data being received on the ground, that the spacecraft had died, it crashed into it. So we can take a look here. We've already seen that. So we can take a look here and see that this is the asteroid, what it looked like as the last frame where it filled the whole view. And I'll show you what I was talking about here. This stuff down here, that's sticking up into the sunlight. And the sunlight's coming from the upper right, kind of. Not completely directly. It's kind of behind us as well a little bit. So that must be an enormous cliff or a rock or something that's sticking up into the sunlight. So very interesting. I will never know what it looked like originally. because it turns out that this little asteroid is forever changed. Here's the second to last photo taken. The last one was just that one little strip. And a human on this scale is about from the one end of the rock there down to the bottom there. That would be about 6 feet long. So these are some very big boulders. These are some really big chunks of rock down there, but there's also smaller ones down in there. You can see the scale, it gets quite powdery. Now, upon close inspection, this is what was left behind on the surface. So, I like the meme somebody made after hitting an asteroid at 14,000 miles per hour to see if it could be knocked off course. This is what the James Webb Telescope saw. Well, not quite. I will show you what the James Webb Telescope saw. This is what ground-based telescopes saw. So yeah, that is just a spot of light with a pair of asteroids, and this plume of material came blasting off the surface and could be detected easily with small telescopes. All you needed was a moderate-sized telescope and a dark sight and know where to look, and you could make a movie like this. So pretty incredible. They did send a CubeSat along with it. So there was a small satellite behind the mission trailing along, and this is the picture the CubeSat got. So it saw the bigger asteroid and then streamers of material coming off of the small moon. Turns out that that is expected when you do physics and you do tests with launching high-speed impactors into batches of sand and grains and things, that this, when particles interact, they will make streams like this. And it's eerily familiar of things like the lunar rays. If you've ever observed the craters on the moon, rays appear and long streaks of lighter colored material can be seen. And this is indicative of, even on a smaller scale, that that phenomena happens. So we're learning about it. Here are the Hubble Space Telescope and Webb Telescope images. On the left is Hubble in the blue, and on the right is the Webb Telescope. So both of them are looking at different wavelengths. Hubble, I think, is actually looking kind of in the blue, if I'm remembering that filter. And the Webb is looking at a longer wavelength there. It's in the infrared, of course. Now let's look at a couple of movies. They actually made little movies from the Hubble. So you can see these 3 frames they put together and how the structure of that material flying off of that little moon is changing. And then the Webb is even more interesting. JWST, you can see almost what looks like a gas flowing off. So the particles of dust that the infrared puts off. So very, very interesting. And this is crazy. This is, it actually formed a 10,000 mile long tail of dust and debris. This was actually taken, as you can see there, down by Christian Sass, I think is how you say that, and Blake Estes. Blake is a former employee of ours at Griffith Observatory, and we all care for him very much. He's down in down under at the moment, still working down there on much bigger telescopes, exciting things. But he took this with his own telescope, and they tracked it for a little while as well. So the stars are going by, and it gets you a better image of that little asteroid that, well, we aren't quite sure what happened to it, to be perfectly honest. We thought it might take a few days to get the period back to see if the orbit had changed, but maybe there's just so much dust and debris in the way that they don't have a good answer yet. Maybe we pulverized this thing so much it blew it apart completely. We don't know, but this is why we run these tests. Now, the Europeans, kind of in an exciting way, have decided to send a spacecraft there to go actually take a look. So they're going to launch this, and I think in 2024, and Hera is going to fly out to this asteroid pair, if it's still a pair, and take a look at the wreckage afterwards. So
I think it's the insurance claims adjusters.
Yeah, it very well could be wanting to know what happened to see if they need to pay the full amount or not on that policy. So in any case, this is important work. As much as we like to joke about things, if one of these were headed our way, this would be big enough it could, perhaps destroy a city. If an even bigger one hits, it could knock the climate even further off kilter than it is now and really create a bad day. We can't live without our environment being stable. We don't want to go the way of the dinosaurs, but we have a space program. So we're finally taking some steps to see, do we have what it takes to move an asteroid out of the way? So the DART mission took a big step in that direction. Quite exciting.